Is it recording? Okay. I think it's recording now. Is that you guys see my screen all right?
Yes, sir.
All right. So I wanted to talk just a couple minutes today about cryptography. This is a topic that I think I've heard a long time ago, and I kind of find it again and again that's kind of useful. So I thought it might be useful for other people to hear. I'm going to try and be fairly non-technical. This is going to be kind of, although cryptography is kind of a technical thing, but I'm not going to be very like command line specific or anything with this. I'm trying to be agnostic to any of the tools or specific programs that are used. So I wanted to start a little bit by talking about a couple of definitions when we're talking about cryptography. So plain text, you use that term. That's usually the original unencoded data we're talking about. And then to encode the data, you use what's called a cipher. And a cipher is a combination of the algorithm that's used and the key that's used to encode it. And then when you take your plain text and apply a cipher, you come out with ciphertext, which is kind of the gibberish encoded data that you see. It shouldn't make any sense to the observing eye. So I wanted to start a little bit by actually spend a little bit of time talking about the history of cryptography. This kind of helps to build up to how sort of some of this works. And so people are probably familiar with some of these basic, like very, very primitive cryptography methods. So the easiest and simplest one is called the Caesar cipher. This is one that I think gets the name because it was used by Julius Caesar when he was around. But you see these things sometimes in newspapers called cryptograms, and essentially each letter, like the letter A, might be converted to the letter Z. The letter B might be converted to the letter Y, and C might be converted to an X. And that's not those. I put those in order. They're not necessarily in a particular order. They could be like randomly assigned. So A could be B, and B could be, X. So any kind of weird combination of letters, and you end up with something that looks, sort of like a gibberish. But then when you apply and like reverse, you do a simple kind of reverse from one letter to the other. It's pretty easy to get back to the original, the original plain text of what you're looking at. And all that's really needed is basically 26 character combinations to get back from one. You might call that the key, is the exact list of which letters go back to which letters. So these are often solved by language experts and by character frequency. For example, in the English language, if you know the letter E is the most common letter, you just go through your crypttext, find out the most common letter that's in there, and so start substituting that out with E. And then you kind of use some logic with that, along with like specifics about the language. If you're looking for the word "the" sort of frequently in there, and sometimes character spacing can sometimes pick out and help you reverse those. That's one people are fairly familiar with. It's been around for a long time. The next one is sort of the same kind of concept, but it's got sort of a rotating key. So instead of having just like 26 combinations of pairs, this one sort of has like 26 times 26. And essentially, you have what would be like in this example I pulled off of this page that was referenced at the bottom here, the word gold medalist. And they use the word Olympic is the key. And so you can see Olympic sort of repeats here. And then if you look up in the chart, find the G where it interacts with the O, and you're going to get the letter U, which gets you here. And then that's how you kind of get this encrypted or the crypttext. And then to reverse it is sort of similar. You find where one of them's at and you just kind of reverse it. So this makes the key, quite a bit more complicated. It's not as easy to go through and just do something like a letter frequency to try and reverse it. So it's kind of a little bit more encrypted. And so usually the way that these kind of things were shared is you have basically a book that had a whole bunch of these little pages on it that were like these character mappings. And then they'd share these books around with people so that people could reverse the codes. And those would be considered like the key for those. The next one that's gotten a little bit of popularity with some recent movies and that is like electromechanical encryption. And that basically is a little bit more complicated version of the previous one, but instead of having like keys that are written down on paper, these have keys that were sort of electronically wired into disks. And they would, put these disks into the machines, then they put sometimes a series of disks into the machines. And so when you push the letter A on the keyboard, it's going to light up the letter F or something on on the light up board on top of it. And so the way that they sort of share these is, again, they have this to sort of like share these disks around with people, and then they'd be maybe 5 disks, but my screen share stopped, but they'd be maybe 5 disks, and then they'd keep track of, you know, which 5 disks are used and in which order on each day is sort of an additional way of encrypting them. So that got to be sort of along the lines, these were used in like World War I, World War II, obviously. The Enigma machine is kind of the most famous one of these, used by the Germans in World War II. But that was very, it was determined to be sort of pretty, the Germans thought it was unbeatable. And of course we know from the movie, I can't remember the name of the movie, but how the English sort of solved that. So from there, I lost a little bit of time trying to put slides together, but from there we move on over to like digital encryption. And early digital encryption used, you know, obviously much more computationally intense sort of algorithms to generate these things. But one of the kind of common things about them is that the sender and receiver had to pre-share a key. So they had to have this secret key that could never be seen by anybody. But in order to make it so that the communication was entirely secure, they had to transmit this key securely from one person to the other. So they would encode it with this key and decode it with the same key. And that kind of resulted in sort of these sort of situations. You could think of these as briefcases. You know, this is how like the military would transmit their secret keys to one another. They couldn't transmit it. They'd actually have to have a paper that they'd put in a briefcase and handcuff it to somebody's hand and bring it across the country. And then once that key is sort of transmitted securely and stored on the other side, then they can communicate securely using one of those encrypted keys. But they still had to basically get the key from one point to the other securely. What was invented, I think, in around 1978 or something, was something called asymmetrical ciphers that use a public and private key. Now, this made a huge difference in the world of cryptography, because instead of now pre-sharing keys, what you can do is you can publish. There's a complex sort of mathematical scheme. I don't know all the details that are involved with it, but they create a combination of a public key and a private key. So they're mathematically somehow coordinated, one with another and related to one another. But what you can do now is you can safely publish your public key, and you keep the private key completely private. And that way, people who want to send encrypted messages to you can take your public key, and then use your public key along with the plain text that they want to send to it, and they can encrypt a message using your public key that can only be decrypted with your private key. So this kind of changed a lot of what we knew about cryptography, because now instead of pre-sharing keys, we can actually encrypt messages to people without having to securely transmit a key to them to begin with. So it's opened up pretty much the world as we know it as cryptography. It's kind of pretty amazing. So there's a few interesting things that public-private key encryption allow now. So the sender, if you want to send a message to somebody, the recipient can publish their certificate key in any manner of forms. Perhaps via DNS, during like an SSL or TSL handshake, it's published during that handshake. In the world of like email encryption and GPG, there's things like key servers that will transmit and publish keys. So the keys can be sort of published, and then the sender can encrypt the data with a public certificate, and it can be once we've encrypted the data in the ciphertext, it can be transmitted in the open, and then the recipient uses their private key to decrypt the data. That's kind of, when we talk about most of what we deal with in encryption today, that's kind of the pattern that it follows. There's a couple of things that this also enables that we don't sometimes realize that it's because of public-private key encryption. But you can use the recipient, so as a sender, you can use the recipient's public key to encrypt data. That's kind of the most common use case. But the other sort of case that we don't see very often is you can use your own private key to sign a message. So you can take a plain text message, and using your private key, you can then publish a signature for that message. And then what a sender or a recipient can then do is they can take the message that was received along with your public key, and they can validate that the message was not changed in transit. That's a kind of an interesting case that has some interesting complications or some interesting applications that enables things like cryptocurrency and things like that as well. And then obviously recipients can decrypt the key with their own private key. So if we think about now, we can transmit messages to people without them pre-sharing the key. The trick then becomes we don't know whether or not people's public keys that they've published are actually belong to them. And I like this quote: "You don't know who to trust. If you've seen Sneakers, you might actually get the reference." But so there's a number of different ways we have now of validating that a public key belongs to the person who we intend. So those have to do with things like SSL certificate chains. So as what a certificate chain does is your computer is shipped, or you can choose which sort of root certificates you want to trust, and then a certificate chain is published by like a certificate authority, and they will sign. They will use cryptography to assign using that sort of public-private key method certificates, so that you can trust the people that they trust, essentially. So we can get a lot more technical detail than that, maybe a future thing, but that's kind of a high level. Another way of sort of deciding who you can trust are things like GPG signing. So this involves a technology or a sort of method called the web of trust. And the web of trust is basically a way of saying if I know Brian and Brian knows Travis, then Brian can sort of sign Travis's key, and I can see that. And when Travis tells me his key, I can see that it includes Brian's certificate or Brian's signature on it, and therefore I can trust Travis, sort of indirectly because of this web of trust technology. And then there's also some things like in, I know, like domain keys and DKIM, as far as like email sending technologies. They use things like DNS to publish public records, and then and that can be another way of transmitting sort of public keys as well. So I didn't have a whole lot of time to go into a lot more detail with that, but there was one more thing I sort of wanted to touch on, and that is in things like SSL certificate novate. When an SSL connection is established, one of the things that we don't sort of realize that happens in that establishment is once we exchange our public and private key, what happens in the SSL session is we actually generate a synchronous token, or like a one-time use throwaway token inside of that, so that the rest of the session is encrypted with a synchronous method. So we don't, since the public-private key thing is a lot more computationally intense, we basically just use the computationally intense part to generate a key that can be used for synchronous, or like it's got the same key on both sides for the rest of the session. So that's a technology that's used in like this SSL TLS negotiation. It's also used like when you send out an email that's encrypted with GPG. And if you send that to multiple recipients, instead of encrypting it for every recipient, all we do is we use the public-private keys to generate a one-time key just for that message. The message is then encrypted using that one-time key, and then what we do is we actually encrypt that key with everybody else's private key, so that they can decode the key out on their own, and then use the key for the actual document to decode the actual document. That probably gets a little bit confusing. I need to make a little chart for it, but one of the lesser sort of known things about that. Anyway, I can see I've taken up 15 minutes now, so I will give it up. If you guys have any questions, feel free to ask.
Thank you very much. That was good, Brandon.
That was really a lot of data to throw in 15 minutes. So
yeah, I agree. This is the type of subject that I need to hear about multiple times to really soak it in.
Yeah.
You know, the breadth of what you code. But yeah, so the public-private key pair we were talking about, when it was just asymmetric, where the military had to carry this key across the country in a briefcase. Mm-hmm. I mean, even if it's the public-private key pair, you still have to transport that private key securely, like from one end to the other. Right?
Yes, but it's only your own key you have to transmit. If you're sending, like if you wanted to send a message to me, I could publish my public key insecurely.
Right.
And I could publish that on DNS or send it to you in email or whatever. As long as I keep my own private key private, it doesn't matter. Like you can still send a message to me without you having to know a secret.
Right. Like I guess I was thinking about like if we wanted to Never mind. I'm confused. It makes sense now. I believe
it's a confusing topic. I need to hash out that presentation a little bit more to make it a little bit more. I need to try and fit it down to 10 or 15 minutes. It needs to be less data, I guess, in there. So
there is a talk that I would like to do, and I shared this with Brian. I'll pop this in the Google Hangout link. It's about the SSH connection, like what you're talking about. Let me find where the chat's at. Chat, there it is. And I hope to do a talk at some point. I don't know if it's going to be a tech talk or which one did I just post? There's 2 links.
yeah, I didn't talk about hashes at all either.
There's one that's more technical, and there's one that's a higher level overview, but related to your talk. I hope to talk about this at some point.
Yeah, Brian mentioned something about